Well guys, let's have a look at some variable forces, and we will be able to work our way down to velocities and maybe even displacements. There's just two quick, short, sharp examples for us to do here, just to consolidate our practice, okay? Right, now, what have we got here? We've got a body with mass 5 kilograms initially at rest is acted on by a force F equals 6 minus t all squared newtons, so okie dokie, where t goes from 0 to 6 seconds, alright? We're going to find the speed of the body, the speed, not the velocity, note, after 6 seconds and the distance travelled. Alright, first thing you notice, well I notice anyway, is that f is given as a function of time, therefore ma, which is what f is a function of time, so we will use dv dt as our derivative expression for a. Okay, that would be the first thing I would recommend, and there it goes. Yes, f equals this, therefore 5a, a being this beastie here, equals that one there in terms of time. We don't have to use our other funny derivative expressions for a in this case, with being v dv dx or d by dx of a half v squared. If the thing's given as a function of time, we don't even consider using our funny derivatives for acceleration. Alright? So what have we got? dv dt equals that, yes, okay, and now we're going to integrate that with respect to t to get v. That's going to be easy, isn't it? Do you know what to do there? I hope so, because I think you would make u equal to 6 minus t and then just go from there. Very good, excellent. So yes, we agree with that, don't we? And therefore du is minus dt. Now we've got to get the whole thing in terms of u's instead of t's. Now I've kind of mixed up the variables there a little bit just to make a point. I would never do that with terminals written here, because you've got to be consistent with, if you do have it a definite integral, which we don't in this case, but if you did, you'd have to make sure your terminals were consistent with the variable in here behind the integrand, and you certainly wouldn't be mixing up the variables. Alright, now, having said that, I'm allowed to do it in this case because there's no terminals there. dt now, okay, I need minus dt, don't I? Minus dt to be du, so I'm going to do a little bit of smoke and mirrors here. Very good, got it. Okay, see a minus out there, minus in here, haven't changed anything, have I? Because a minus times a minus is a plus. So off we go, and we get that. Okay, now that's very easy to integrate now. 1/3 u cubed plus c. Now we can substitute back for what our u was. Yes, yes. And we get that. Now it's time for boundary conditions. Very good, excellent. And we get that, and therefore, my goodness, what's 6 cubed? Can you figure that out quickly? Goodness, what's 6 36s? That must be about 216, I think. Yes, so therefore C is that, and therefore V is that, with our thingo substituted in for C up here. That looks like it. Now, is that what we're supposed to do? We probably, yes, but we do need to know whether this thing, the speed after 6 seconds. Okay, well, what would be the velocity after 6 seconds? Yeah, okay. Well, if that's the velocity, that's going to be the speed, isn't it? Most definitely, because the speed is just the size of the velocity, okay? So, yes, what are we trying to do here? The distance travelled. Yeah, this is the next bit. The distance travelled, that's the more important bit. Is the distance travelled the same as the displacement? Has it changed direction somewhere within that first 6 seconds? We've got to get a handle on that before we go plunging headlong into distance questions, because there's usually booby traps being set for us. But I don't think so in this case. That's the best thing to do. Get yourself a graph of V versus T. I always do that. Looks like V is always positive. It doesn't double back and become negative. Usually with these velocity time graphs, if the thing has crossed over the axis there and gone from minus to plus or plus to minus somewhere within the time interval you're interested in this case 6 seconds, that's when you've got to be very careful, because the velocity will have changed direction and therefore the thing's turned around, and therefore distance is no longer the same as displacement. But in this case it is, so we can just breathe a sigh of relief. So take that first 6 seconds, that's all we're doing. Therefore, the distance equals the displacement, no change in direction, all the same direction. So therefore, we're going to start integrating again now. to get our displacement. There it is. Is that right? Yes, 1/4 of that stuff all to the fourth, I mean, plus this one with a t there, plus another constant of integration there. Now more boundary conditions, I think. Oh, I just cleaned up a bit, did I? Yes, okay, Mr. Computer, good enough. Now it might be about time for boundary conditions. There we go. Alright, so what are we going to get out of that? Well, that's very interesting, isn't it? So if you made t naught, that'd be -6 to the fourth. My goodness, whatever that is, 36 times 36, and apparently divided by 60, that'll be a zero term. And therefore this one here, if you solve it for d, you must get -21.6. Oh, how very fascinating. There we go. That's what x is. Now we've got to work out the distance travelled in the first 6 seconds. So we substitute t equals 6 into the beast, and we see what we get. Very, very nice. Oh yes, because this becomes 0, doesn't it? Ah, ha-ha. There you go. So we just get that and that left in our displacement expression, and we get that. So that's our distance, which is also equal to our displacement. Thank you, Mr. Box. My goodness, how satisfying. So that's how far it travelled, distance, in the first 6 seconds. Right, off we go again. This is a second of 2 in this short, sharp and terrific little video on variable forces. Now, a particle of mass 3 units, 3 something or others, we don't know what, moves in a straight line, and at a time t its displacement from a fixed origin is x. Yes, at time t, that's alright, and its speed is v. Righto, the resultant force is 9 cos t. Okay, that means accelerations in terms of time as well, because F is ma, as we know, and we've got v is 2 and x is 0 when t is 0. Your boundary conditions in terms of time, everything looking good. So this will be easy. We've just got to work our way down to displacement from the force and hence the acceleration, so it'll be anti-diffing twice with trig functions. Yes? There we go. F is 9 cos t, that means that 3a, because the mass was 3, 3a equals 9 cos t, solving for a. That's the first bit. Now we know that a is dv dt, so now we can integrate with respect to time to get v. There it is, and what about our boundary conditions? Yes, there we are. Is that right? Did I do it right? Yeah, v is 2 when t is 0. Excellent, there we go, and it looks like c is 2 as a result of that. Because, yes, this term here would be 0, sine of 0 is 0. So therefore we've got our expression for v, everything's looking good. Now we have to anti-diff again to get x in terms of t, don't we, guys? We do indeed. So that's anti-diff now. There we go. So now, derivative of the antiderivative of sine is minus cos, so that'll be minus 3 cos t plus 2t plus another constant of integration, which we'll call d. Looks like boundary condition time again. There we go. So now, how did we get that? Goodness me. X is 0 when t is 0. That's right. So 0 equals minus 3 cos 0. Cos 0 is 1. That's right. Yes, that term's 0, and then that one there. So we get d is 3, I think. Excellent. So therefore, there is the final result. Well, wasn't that easy? Easy peasy. It certainly was. All right. You happy? You're getting confident? That's what we want to hear. Now, let's do B and hope that doesn't make us unconfident. Let's have a good look at it. All right, the resultant force is 3 plus 6x. Okay, you get your radar up when you see them not in terms of t. So 3 plus 6x, is it time to trot out the funny derivatives or not? The resultant force is 3 plus 6x. The way you find out is you do your boundary conditions. See what they are. V, okay, they're in terms of V, yes, and X. There's no time anywhere. Okay, this one qualifies for the funny derivatives. It does, okay. Now, which one? Which funny derivative for acceleration? We've got the force, and therefore the acceleration is in terms of X, okay. So if it's in terms of X, we use d by dx of a half V squared. If it's in terms of V, we use v dx, okay? Do you see how I did that? It's just a process of elimination. It's a cookbook procedure. You've got to keep doing it to get good at it. So there's our force. That's yes, that's 3A. Therefore, A is that. Now, I'm going to trot out my funny derivative now. Yes, thank you, Mr. Computer. We worked that out, didn't we? But thank you for telling us. There's A is d by dx of a half v squared. Yes, ain't it grand, guys? Ain't it grand when you get some right? So, where are we? Yes, that's right. Now we're going to integrate with respect to x, aren't we? This is interesting because we're going to have to take a square root here, and you always have to be very careful when you're taking square roots to get v, because you get these spurious solutions. So we'll see if we do in this case. Right, a half v squared equals, now I've integrated, that gets you an x, that gets you an x squared plus a constant of integration, so it's boundary condition time. And we sub that in, okay, so off we go. It looks like c is 2. That makes sense, doesn't it? Because a half of 2 squared is 2, so 2 equals 0 plus 0 plus c, therefore c is 2. Righto, that's what we've got now. So we've got to get to v, because we're trying to work out what v is when x is 2, alright? Now, that's where we're at, so we better solve that for v, and then be jolly careful with what we get. Yes, alright, now that's okay, but one of these, as I keep saying, one of these solutions is likely to be an imposter. And we find out by using our boundary conditions. So v is 2 when x is 0. Now, that's instantly telling me, look, 0, 0, okay, now 2 2's are 4, and the square root of 4 is 2, so this is telling us that v would be plus or minus 2, which is absolute rubbish. It's plus 2, so can you see? We've got to chuck out one of those spurious solutions. Yes? That's right, v is 2 when x is 0, so we reject the negative solution and we know that therefore v is this little baby here, this one, this is the one we want. Now, having confirmed that, we can now, with confidence, plug in our value of x equals 2 and get a value for v. There it is. What is it? Square root of 2. Yes. Does that all look right? Yes, it does. So what's that come to? Good heavens above. 2, 4 is 6 and 2 is 8. 2 8s are 16. Square root of 16 is 4. Looks like v is 4. Ha ha. Very nice. Do you like it? Yes. I think that might be the end, and the end is your friend, as is the trend. But I haven't got a star for you tonight. I forgot. I'm sorry about that, but you are a star, huzzah, and you will go far, I can assure you, if you do some practice. Well, we got out of that in under 13 minutes. What a record. I hope you have a wonderful day, and I'm going to get out of here and have a nice cup of tea and a relax. I'll see you later.